All right, here we go. So we wrote the improper integral here, but we always need to find the indefinite integral first. So at this moment, you can start thinking about like what kind of like strategy you should follow to integrate this. To me, it looks like integration by parts is the best strategy. So, but you can pause the video and keep thinking about it before you move forward. So I'm going to go ahead and then choose ln x to be u, because ln x against a polynomial type function. Here you have 1 over x to the p, so it's almost like x to the minus p times ln x times dx, right? So x to the minus p against ln x, I call ln x to be u, and du is going to be dx over x, and whatever left over here is your dv. Sorry, this one, dv, right? So dv is going to be x to the minus p times dx, and I'm going to use the power rule for integration. So x to the minus p plus 1 minus p plus 1. Okay, so let's go ahead and write down the uv minus v du. X to the minus p plus 1 minus p plus 1 times ln x minus v times du. Okay, so if you look at the description of du, it's like dx over x. So it's essentially x to the inverse, x to the minus 1 dx. Okay, so x to the minus 1 times this term, we're going to add the exponents here, so you're going to be careful. Okay, so x to the minus p plus 1 times x to the minus 1 is x to the minus p, so you have minus p plus 1 dx. Okay, you're going to be very careful here. All right, here we go. So let's just continue, because I have one more integration to take care of. Okay, I'm going to use the integration by parts again. X to the minus p plus 1 divided by minus p plus 1, but I have another one of that here, right? I have another one of that here. So it's going to be minus p plus 1 squared. Okay. Now it looks pretty good. If I can factor out x to the minus p plus 1 minus p plus 1 squared. Okay. So essentially, this one doesn't have any square, so that means I should multiply this by negative p plus 1, and I should keep ln x, and this is exactly what I factored out, so it's minus 1. So I think this is the best form of the indefinite integral. So I can go ahead and then consider this integral now. All right, so I copied forward the value of the indefinite integral. Maybe I should also put the bracket here, right? So let's put the bracket here. So I'm gonna plug in infinity, but I can't, so I should consider that in the limiting sense. So I'm going to write it as limit as b approaches infinity, b to the minus p plus 1 minus p plus 1 squared here, right? Minus p plus 1 ln b minus 1. So that's us taking care of the upper limit. And the lower limit is going to be minus 2 to the negative p plus 1 negative p plus 1 squared, negative p plus 1 ln 2 minus 1. So I don't need to worry about this term. In fact, it's a finite number. What worries me is this limit here. Okay, I have to sort of like pay attention to that. All right, so I rewrote this term. So you have this part, right? Put the parentheses here. Okay, so you have this part multiplying this quotient first, minus this part multiplying this quotient. So I just split that part. So I just sort of like write this in a very clean way. Okay, and whenever I see b to the minus p plus 1, okay, I wrote it as a reciprocal b to the p minus 1. Okay. All right, so that's sort of like from this line here to this line. Okay, so remember that the limit operation is on B. Okay, so these parts are constant at this moment. I don't need to worry about that, but I have to worry about the exponent of the B terms here. Okay, and this is a very good limit question. You can pause the video and you can pass the limit by using the L'Hopital's rule for the first one, because you have ln infinity over infinity to the power of p minus 1 type form, and if p is greater than 1, if p is greater than 1, so that means these power terms are going to be positive. Okay, so that implies that ln b over b to the p minus 1 is going to be infinity over infinity type indeterminate form. That's why you can use the L'Hopital's rule for the first guy here. Okay, for the first term here, it's the application of the L'Hopital's rule, and after you take the derivative of the top and the bottom respectively, so that will take you to some number divided by infinity. So this term is going to go to 0. Okay. Whenever p is strictly greater than 1. Okay, if p is 1 or if p is less than 1, you're talking about just the limit to be infinity, so everything diverges. Okay, so p has to be greater than 1 for this term, for the first term, to converge to 0. And here the same deal is happening. Okay, if p is greater than 1, p minus 1 here is positive, so it's like 1 over infinity to the power, which is positive, right? So that's going to be 1 over infinity, so this will as well go to 0. When again? When p equals when p is greater than 1. If p is less than 1, I can't do that trick. Then you are going to have b coming with a negative power. That's not good. Okay. If p equals 1, we're still safe. But for the second term here, for this term here, but not for this one. Because if p equals 1, we still have ln b at the top, and as b approaches infinity, that diverges. So p has to be strictly greater than 1 for both terms to be 0. So going back to here, I can go ahead and write down that this term is 0 as long as p is strictly greater than 1. Okay, and then the leftover term here is finite, so that I can go ahead and conclude that this is finite. So in other words, the improper integral converges. So is the infinite series, but as long as p is strictly greater than 1. Okay, so going back to the original problem here, I have the integral here converging. So is the infinite series. So I can go ahead and conclude that this series is convergent if p is strictly greater than 1. Because the question was asking me to find the p values. Here we go. If p is strictly greater than 1, I don't know, I don't care what it is, but as long as it's strictly greater than 1, we have the convergence. Right, for this infinite series, it's n, 1 plus n squared to the power of p. And remember that p is positive, by the way. We don't know exactly what p is, but p is positive. For what we're trying to find the p's for which the infinite series converges. You can check to use the integral test, but the decreasing condition will not hold true. So you won't be able to apply the integral test for that. I think the best strategy for this infinite series is to use the Nth Term Test. Okay, Nth Term Test. So Nth Term Test is to prove the divergency for the given infinite series, and we check the limit of the nth term. Okay. Well, if p is positive, when n goes to infinity, well, this is already going to infinity, and this term is going to come with a positive power that's diverging to infinity. So infinity times infinity is going to diverge infinity. So the nth term test says, like, if this limit is infinity, then in fact, not necessarily infinity, but if it's not 0, then nth term test concludes that this is divergent. Okay, we didn't need to use the integral test. In fact, integral test would probably fail because an is not going to decrease. This is not a p-series, so I can't use the p-series test. So we're using a test that we learned earlier. That's called the nth term test. That's again used just to prove divergence and not for convergency. And then, since I thought that these terms for increasing n are increasing, so I thought that nth term test is the best one to go with. If you have any other suggestions or something, just please let me know. But I think this is the easy way to prove that the series is divergent. All right. That makes it the end of the video. Thanks for watching. I'll see you in another video. Bye.